Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series, which is intended for the BSc Honours Physics students. We have been going through the section on optics. We have seen a course of lectures in the area of diffraction. In the area of diffraction, we saw the definition of diffraction, and then we tried to explain the rectilinear propagation of light to a certain extent. In this lecture, the contents include explanation for the formation of shadows using wave theory, half-period zones, resultant intensity inside the shadow, diffraction of sound and light waves, plane diffraction grating. And so in principle, the lecture can be divided into 2 parts. One is explaining how you get complete darkness inside the shadow region. We have discussed this in a great detail in the last lecture also. So let me let me give you the salient features with regard to this phenomenon, and then we'll move on to diffraction grating. In the last lecture, I told you that when light is coming from a source, you have a spherical wavefront, and a part of it will be a plane wavefront, and the plane wavefront was divided into what are called half-period zones. By half-period zones, as I told in the last lecture, what we mean is the path difference between 2 successive zones will be lambda by 2. Therefore, the light coming from the first zone will be opposed by the second zone, because the path difference is lambda by 2. If light is coming at a given point P from the first zone, if it leads to a crust, then the light coming from the second zone will lead to a trough. Therefore, the successive zones will be opposing each other, crust, trough, and the third zone again will be a crust. So alternate zones will be adding, whereas the successive zones should be getting subtracted. These things we will see in the mathematical formulation. The second point is the obliquity factor. The higher the zone, you have the first zone, second zone, third, and so on, the displacement caused at P from the higher zones as you go from the first to second, third, and so on, because of what is called the angle of inclination theta, which is made by the light coming from the various zones, the displacement caused at a point P will be smaller and smaller. So the higher zones will give rise to only very small intensity, and the highest zone, if you go to infinite zone, the intensity cost will be equal to 0. So these 2 factors that we kept in mind, they are the half-period zones, and I showed that the area of the first half-period zone to be equal to pi b into lambda, b the distance separating the source and the point P, where we calculate the intensity. What about the point P? Where is the point P? P is a point inside the shadow, and we want to show that the intensity at the point P is equal to 0 in spite of the fact, when we are talking about diffraction, light should bend. In spite of the fact that the light beam is bending, still the intensity should be shown to be equal to 0. This is a difficult task. It is a challenging task for the physicists who proposed the wave theory of light. Anyway, this is a very important problem. Here, you look at this expression here, you got pi b lambda plus lambda square by 4. This term is neglected. This being small, it is neglected, then only you get the area of the zone to be equal to pi b into lambda. The second zone and third zones, all of them will have the same area. This is one of the points to be remembered. All the off-period zones will have the same areas. The second thing is the radii of the first, second, third zones will be having this kind of expression. R1 will be equal to square root of b into lambda. The radius of the second off-period zone will be square root of 2 times b into lambda. So, the natural numbers 1 times b, 2 times b into lambda. So, the radii of the different annular rings will be directly proportional to the square root of the natural numbers. This is another point to be remembered. So, the areas are all equal, the zones are all equal. The radii of the first, second and half period zones will be following this kind of relation, square root of 1 into b into lambda. The second zone, the area will be square root of 2 into b into lambda and so on. The radii are proportional to the square roots of the natural numbers. Then again, as I told you, the points to be remembered are the area of the zone is an important factor in deciding the intensity of the point P. The distance is another point to be remembered. Then the third one is the obliquity factor. That is the distance of P from the wavefront is 1 point. That will decide the intensity at the point P. The area of the zone, as I told you. The thirdly, the obliquity factor. What is oblique means? The higher the zone, the angle subtended by light coming from the third, fourth, fifth and so on, those zones will make a larger angle, and so the light coming from the higher and higher zones will cause a lesser displacement at the point P. So, because the zones are called half-period zones, that means light coming from the first zone will be opposed by the light coming from the second zone. What do you mean by opposing? The first zone, if it produces a crust, the second will give rise to a trough. Third again will be crust and so on. So, in the picture to come, I will show that the displacements caused or the amplitudes of vibration of light coming from the first, second and third zones or M1, M2, M3, etc. They are the secondary waves coming from the different half-period zones. Then you have the obliquity factor. Therefore, the quantity M1 will be greater than M2, that will be greater than M3, and so the higher zones will give rise to lesser intensity or lesser displacement. So, because the obliquity factor, the displacement cost will be continuously decrease. That is what I am showing here. You see the light coming from the first zone, that is M1, that is your amplitude. Then the light coming from the second zone is M2. Why the arrow M2 is drawn downward, whereas M1 is upward? M1 is upward, that means the crust. M2 is downward, that means the light coming from the second zone gives rise to a trough. They will oppose each other, as I told you, because the path difference between the two light beams is lambda by 2. A path difference of lambda by 2 will correspond to a time difference t by 2. That is the reason why they are called half-period zones. So, the light coming from the first zone, if it leads to a trough, the second will lead to a crust, a trough, crust and trough. So, therefore, the displacements caused by the light coming from the first, second, third, fourth and so on, they will be opposite in direction. Crust is upward, trough is downward. The second point is the amplitudes, as I told you just now, because of what? the obliquity factor, the amplitudes of vibrations M1, M2, M3, they will keep on decreasing. When you go to higher and higher zones, the displacements caused at a given point P will start decreasing. These two factors have been taken into account and they are incorporated and they are shown diagrammatically as you see here. So, M1 is in the upward direction, M2 downward, M3 upward, M4 downward and so on. Then again the displacements are decreasing. So, M1 is larger and then you go to M8 or something, it is coming down. So, at very high zones, the light coming through those zones will be very small, and in the end I will show the nth zone when n goes to infinity, that will be equal to 0. Obviously, the way in which the displacements are drawn, the very high zones will result in very low intensity or very low displacement. Okay, that is what we have. Now, therefore, M1 is greater than M2, M2 is greater than M3 and so on. Now, again the phase difference of pi, that is the reason why they will be opposing each other, constructive, destructive and so on. Okay. So, we have M2 will be equal to M1 plus M3 by 2. Now, what is M2? M2 will be between M1 and M3. The example is the following. You say that you have this M2 to be equal 4. Equal 4. What is this? This is 5, 5, 4, 3. 5, 4, 3. So, you sum up M1 and M3 divided by 2. 5 plus 3, 8. 8 divided by 2 will be 4. That is your M2. That is what I am showing here. M1 plus M3. M1 is 5. M2 is 4. M3 can be taken as 3. Then M2 will be M1 plus M3 by 2. 5 plus 3 by 2. That will be equal to 8 by 2, that is 4. That will be equal to M2, right? So, because the displacements are gradually decreasing, M2 obviously can be expected to be the average of the first and the third. Okay, that will be made use of to simplify the mathematics that you are going to come across here. So, the resultant amplitude at the point P at any given instant of time will be M1 minus M2 plus M3, because you know M1, what M2 is opposing. So, minus M2, then again 1 and 3 will be supporting each other. Again the arrow is upward, M3, then minus M4 and so on. So, that can be written as M1 by 2 plus, you take this M1 by, the remaining M1 by 2 here, minus M2, then plus M3 by 2, then plus half of this will be here, minus M4. You tell me now what will happen to the expression that you got here. I told you that M2 will be equal to M1 plus M3 by 2, right? M2 is equal to M1 plus M3 by 2. That is what you have here. M2 is equal to M1 plus M3 by 2. Therefore, what will happen to this term? What will happen to that term? The term inside the bracket will become equal to 0. Therefore, when you are trying to find out the resultant intensity is nothing but it is directly proportional to A square, the amplitude square. We are trying to find the resultant amplitude, that is given as M1 by 2 plus M1 by 2 minus M2, etc. that you see here. What I would like to impress upon you, the value of the terms inside each bracket will become equal to 0. Okay, this bracket will go to 0 value. This again will be 0. You can cancel. Okay, the resultant displacement finally turns out to be simply M1 by 2. Okay, that is important point. So, in spite of the fact the plane wave front has been divided into what? Number of half period zones, first zone, second zone, third zone and so on. The displacement caused by the light coming from the third zone, second zone, third zone, fourth, fifth zone, these things they become 0. The resultant amplitude is nothing but half of the displacement produced by the light coming from the first zone. Only the first zone is important. Okay, the first zone, you have a plane wave front, you have got a first half period zone, right? So, your resultant displacement that you got here, M1 by 2 plus ultimately you can have for the nth zone, you will have M1 by 2. okay, m1 by 2, and n is odd if n is even and so on, right. Therefore, these values what? As I told you, the displacements caused by the very high zones when n goes to infinity, what will happen as a resultant displacement? Those zones will not become equal to 0. The light coming from those zones will give rise to only 0 amplitude. Let us have a break at this point. Welcome back at the break. Now, we have been trying to determine the resultant displacement and hence the resultant intensity that will be found inside the shadow of an object. And we want to prove what? What do we want to prove? We want to prove that even though light undergoes diffraction and around the edges of the obstacle, even then the intensity that is produced inside the shadow region, what will happen to intensity? It should be 0. It will be almost negligible or 0. That is the reason why shadows are cast, or the intensity of the light in the shadow region is 0. You have darkness. That is what we are trying to prove. So, what was shown by Huygens, Fresnel and all, they divided the plane wave front into a number of half period zones, and they found out the displacement caused at a point A due to the light coming from the different zones, first, second zone, and showed that the resultant amplitude is essentially equal to m1 by 2, because the other zones, as I told you, they annul each other. The light coming from the other zones, they annul each other, and not only that, the displacement caused by the outermost zone, when n is become equal to infinity, the displacement caused will be very negligible or it is 0. Therefore, the last term can also be omitted. So, finally, what turns out is the displacement will be m1 by 2, the half of the displacement of light produced by the beam coming through the first half period zone. So, the important point to be remembered is the resultant displacement caused at a given point P. When you have an obstacle, the intensity will be m1 square by 4, because intensity is nothing but it is proportional to amplitude square. If amplitude is m1 by 2, the intensity will be m1 square by 4. Therefore, the resultant intensity will be m1 square by 4. Okay. Now, what about the obstacle? When you have got a plane wave front, the light coming from the plane wave front, and the intensity caused is m1 square by 4. And if you place an obstacle, the size of even a small obstacle will be able to cut or will be able to obstruct light coming through 50 off period zones or 100 off period zones. However, the light coming from the first off period zone will be cut completely. No light will be, because even if you take a very tiny obstacle, the light coming, because the first zone is a central zone, the light coming from the first zone will be obstructed. Therefore, your I will be equal to 0. So, the essential thing is the intensity at P is only 1/4 of that due to the light coming from the first half period zone alone. That is important. The light coming from the second and third, I showed effect due to the terms inside the bracket, they become 0. Therefore, only half of the area of the first half period zone is effective in producing the illumination at the point P. I have wantonly changed the color of the font to show that the intensity at the point P will be due to the light coming from the first half period zone alone, as I told you here. Then, if you are placing a minute obstacle, a small obstacle of the size of a pin, even that obstacle is sufficient enough to obstruct the light coming from or passing through the first half period zone. Let me read once again for you for your benefit. A small obstacle of the size of the area of the first half period zone placed at O will be 0. Even the small obstacle will be able to obstruct the light or will cover the light coming through the first half period zone. So M1 will be 0. Okay, it will cover means M1 is 0. Therefore, intensity will be equal to 0. Therefore, when you have an obstacle, when you got a light beam, I have a pencil and I got a paper, I get the image, and it is easier to explain the so-called formation of shadows or the rectilinear propagation of light. What is rectilinear propagation of light? Who gave the rectilinear propagation? It is Sir Isaac Newton, who said light travels in the form of rays. So if it travels in the form of rays, the image cast on the wall or the shadow produced on the wall could have been easily explained without going through the wave theory or half period zones and so on. So the wave theory, the people who propounded wave theory found it extremely difficult and they had to bring in new concepts, the spherical wavefront, plane wavefront being divided into half period zones, how they annul each other, and finally explain and obtain the final result, namely, even if you got an obstacle here, light is there, the intensity cost here will be 0. I is 0, that is what I showed you here. The light is coming essentially from, the intensity is coming from the light coming from the first half period zone. Okay, M1 square by 4. M1 is the amplitude of light coming from the first half period zone. A boy of this size, a person who is standing here, he will be obviously able to cut the light coming from the first half period zone, and that's the reason why the intensity here becomes 0. Intensity becomes 0 means what? It is darkness. So the darkness or the shadow that is produced because of the fact that a boy or a girl is standing in front of the light, in spite of the fact light undergoes diffraction, the light bends actually at the edges of the person or edges of an obstacle, or it may be pencil or whatever be the obstacle that you are placing in the path of the light beam. In spite of the fact that diffraction means bending of light beam, so light beams bend, but in spite of the fact they are bending, the intensity can be shown to become equal to 0. That is how we explain the formation of shadows. That is a major success of the wave theory of light. While considering the rectilinear propagation of light, the size of the obstacle used is far greater than the area of the first half period zone, and hence the bending of light around corners cannot be noticed. Light beams bend, but even if there is a bending, that doesn't give rise to any intensity, or the intensity cost becomes equal to 0. Hence, it looks as though light travels in straight lines. Okay, I will read for your benefit the contents of this slide. While considering the rectilinear propagation of light, the size of the obstacle used is far greater than the area of the first half period zone, and hence the bending effect of light around the corners, the diffraction effects, will be extremely small. The intensity of light in the shadow region is insignificant or 0. We showed mathematically it becomes 0. It is insignificant, and so even though light beam bends around obstacles, there is diffraction is there, but the intensity produced at the shadow region is negligibly small or 0. So it looks as if light travels in the form of straight lines, as was assumed by whom? By Sir Isaac Newton. That is how he explained the formation of shadows. That finishes the first part of this lecture. I will pass on to the sound wave diffraction, and I want to explain to you why the TV signal is not received in hilly areas. One or two slides I have shown at the beginning when I talked about diffraction phenomenon. It is bending of the beam. The bending of the beam, when sound is produced, when I am talking here, the person in the adjacent room can hear how the person in the adjacent room is able to hear me, because he is interested in what I am talking. So he is able to hear. He is able to hear the conversation because of the fact that the sound wave has got a longer wavelength and it can easily bend, right? The sound wave got a longer wavelength, and so the sound made by the students here can reach the ears of the teacher or anybody walking in a veranda. The person is not in sight with the people who make sound, but the light beam, the sound beam interfere, or it shows diffraction, it is bending, and so because of bending, the sound is coming out. So sound bends, light also bends. But when you go to the radio signal, the bending is easier, and so the visible light waves are tiny, less than millionth of a meter in length, and therefore we can see light that comes directly towards us, right? Radio waves are much larger, like sound waves. Radio waves are much larger and diffract when they pass hills and buildings, so that we can receive the signals. So radio waves are easier to be received at the other end, whereas the TV signal is not often heard because of the fact that the wavelength is smaller. Radio waves diffract around the hill to the house. On the other hand, all electromagnetic wave radiation travels in straight lines, and one of the things, the radiation travels in a straight line. Then if there is something to obstruct, it can undergo diffraction. So the radio waves are able to reach from the source of a disturbance, from where it is emitted to the receiving end or to the receiver, whereas the TV signals are not received very much because the shorter wavelength, right? This explains why television waves are much more difficult to receive in hilly areas than the radio waves, which have a longer wavelength, and that is why diffraction of light is so difficult to observe. So light diffraction, because the wavelength is smaller, the diffraction is somewhat difficult. So let us now go to passage of waves through an opening. When opening is large compared to the wavelength, the light waves do not bend around the edges. That is important, right? When the opening is small, the bending is noticeable. The bending, the opening should be small. When the opening is very small, the waves spread over the entire surface behind the opening. The second point is important. When the wavelength is small and is comparable to an opening, then the light beam will bend. So in the next section, we make use of this particular principle which I told you. If the wavelength is small and comparable to the size of the opening, then the light beam will bend. Now we talk about plane diffraction grating. You all know about the passage of light in the case of Young's double slit experiment. We had a source of light. You got one slit here, opening here. Then we have two slits, S1 and S2. You would have studied long back, or I would have given a talk earlier with regard to the passage of light through two slits, or it was shown first by Thomas Young, who showed that light coming through two openings or two slits will interfere with each other, giving rise to what is called interference pattern. Similarly, here we are going to have 15,000 openings. How many openings? 15,000. If you take a diffraction grating in the laboratory, it would have been given 15,000 LPI. That is 15,000 LPI means what? Lines per inch. 15,000 lines per inch. So for every inch, 2.54 centimeter, there will be 15,000 openings, right? You got 15,000 openings. So you got light beam here. I have narrow openings. So as I told you just now, if the wavelength matches with the size of the opening, then the light wave will undergo diffraction. That is what you talk about now, plane diffraction grating. You got a grating, something like a glass, something like a mirror or a glass slab that contains number of rulings, lines drawn, and spacings. The spacings act like openings. In the double slit experiment, you have got only 2 slits. You have got now 15,000 slits through which light will be coming, as a result of which you will be getting what is called diffraction. You will be getting, if you have got a white source, you will be having a green line or blue line depending upon the value of theta. We will see in the next lecture in a greater detail about the plane transmission grating. Let me now pass on to the summary of what I have been telling you all along in this lecture. Number one, even if light bends around obstacles, Fresnel was able to explain the formation of shadows. Second point is, he could show that the intensity of light falling inside the shadow is negligible. This he was able to conclude by splitting the plane wave front into half-period zones. A diffraction grating can be used to determine the wavelength of spectral lines. Now we pass on to the question session. Number one, what are half-period zones? What are the factors which govern the resultant intensity inside the shadow? Give the expression for the resultant intensity. Why television waves are much more difficult to receive in hilly areas than radio waves. With this, we come to the end of this lecture. We will see in a greater detail the functioning of the diffraction grating in the lecture to come. Thank you.